civiltà dell'amore. Fratelli e sorelle, costruite senza stancarvi mai questa civiltà. Lavorate per questo, pregate per questo, soffrite per questo.
Buonasera.
Good evening. Good evening to all the people in the room, and good evening to all the people connected online for this session that is entitled Energy from Nuclear Fusion. Is it possible to imitate a star? This evening's session also addresses two fascinating and important subjects. On the one hand, we consider the reproduction of the physical process feeding stars and making them bright over our sky in a laboratory. And on the other side, we also have another relevant subject, that is the great economic, social, and eventually political importance of how to connect this phenomenon to produce energy that we need in our civilization. So there are two interlinked subjects. One is strictly relating to physics, and the other one focuses on the potential and possible usefulness that we expect in taking advantage of this kind of phenomenon. So energy-related issues such as the availability of resources, the environmental impacts of energy production, and geopolitical tensions relating to supply are considerably present in the media, on the government agendas, and also as a consequence in research and development plans of both public and private institutions. And the dramatic events of this year that started last February, but really considering the situations in terms of energy has been critical for a long time, let's say at least for a large part of European countries. And these events had consequences on energy costs and possibly highlighted even more the importance of these subjects. We should have some slides here in the room right now, and within this context, this year we have seen in the news and on television titles and headlines and news about important results, scientific results in the field of energy, in particular in energy obtained from fusion, and obtained at the Joint European Torus, JET, its acronym, facility that is located in the UK near Oxford. I would like to go through some of these headlines just to emphasize the big impact that this piece of news had. From La Stampa newspaper, the nuclear fusion is closer, record test for the JET European reactor. Or from Rai News, nuclear fusion is closer now, record of energy production in a test carried out in Oxford. Or in the Corriere della Sera, one step forward towards nuclear fusion, new record of energy produced. On La Repubblica, one step more towards nuclear fusion, new record of energy from the European experiment. Also, in international press, there has been a lot of attention for this event. For example, BBC headline, major breakthrough on nuclear fusion energy, or the Wall Street Journal, European scientists set nuclear fusion energy world record. The scope of this news is pretty clear, I think. And the meeting this evening is very pleased to have Dr. Fernanda Rimini to talk about this fact and the meaning that it has, its significance at this stage of research, and also considering the importance that the energy issue has acquired in our civilization. Fernanda Rimini graduated in physics at the University of Milan, and then she worked at the Joint European Torus for most of her career from 1987 to 2000, and then from 2009 to now, with an 8-year interlude spent in France at the Commissariat à l'énergie atomique, which is the Atomic Energy Commission in France. She is an expert in the physics of plasma, that is the state of matter, in which very high temperature causes the total separation of electrons from atomic nuclei, and generating this stage of matter that is unusual on Earth, but relatively common in the rest of the universe, and typically in stars. And she is an expert not only in basic physics of the states of matter, but also in the operations of magnetic confinement machines. That is to say, all those aspects that concern the functioning of those devices that keep the plasma in this high temperature and in stable conditions, using a complex set of physical processes and control technologies to obtain this stability condition. From 2015 to 2021, she served as leader of the group of scientists and technicians responsible for jet plasma operations, which is this high-temperature gas I mentioned before. And currently she is a JET Senior Exploitation Manager, and she is in charge of ensuring the execution of the JET scientific program proposed and led by the European Research Consortium, Eurofusion, and her task basically is coordinating the necessary preparatory activities to carry out the scientific program. In her career, she has made important contributions with experiments aimed at defining the operating parameters for future nuclear fusion reactors, also coordinating the scientific work of many colleagues, including myself, by the way, and she is author and co-author of more than 600 scientific papers published in specialized journals. There is a very important point for tonight's session, well, in general, but especially for tonight's session, and is that Fernanda could take part in the 2 experimental campaigns conducted at JET using the mixture of hydrogen isotopes that enable thermonuclear reactions with production of fusion energy. These were in 1997 and 2021, respectively. And this is one of the main reasons why we decided to invite her here this evening, and one of the main points that we will address in our session. Right. We are going to begin asking questions to Fernanda about her activities that is so important. So what is nuclear fusion and why is it so important? Good evening. Nuclear fusion, as the title says, is what happens in the stars. It is a phenomenon whereby 2 nuclei of lighter atoms combine in a different element, and the combination is such that the resulting element has slightly less matter mass than the original element, and this matter is transformed into energy. So it is a nuclear phenomenon that provides an enormous amount of energy. In stars, such as our sun, this phenomenon is accelerated and favored by the fact that these nuclei are kept close to each other by gravity and pressure. And in the Earth, we are now trying to reproduce this phenomenon, or to obtain fusion, even if we know it will not be exactly like the one in the Sun, because in the Earth we do not have the same conditions. So we are working towards different conditions. Instead of having a very high density and high temperature, we have a very low density and very high temperature. There are two general lines of fusion that we'll talk about. One is inertial confinement and one is magnetic confinement. This is a picture of a chamber of the largest experiment of inertial confinement in the United States. It's called NIF. And magnetic confinement, as Carlo mentioned, we have ionized plasma, so the particles are charged. We heat it up at very high temperature, and to keep this gas ionized and to keep it far from the walls of the chamber, we use magnetic fields, because when there is a magnetic field, I'm sorry, I'm using my hands to explain myself, and when there is a magnetic field, the particles have a motion and they remain attached to the magnetic field, and so we manage to confine them. What you see here is the inside of the tokamak we are talking about, of the jet. That is the machine that we're talking about and the experiment on which I have worked the most. The fusion that takes place in stars has light elements like hydrogen, and as I said, in the Earth we do it in a slightly different way, but we use two isotopes of hydrogen. That one is deuterium and the other is tritium, and we selected these because they seem to have they seem to be easier to manage, and this process with these elements seems to be easier to carry out, and the plasma doesn't really need to be heated that much. And the result of this deuterium and tritium is an alpha particle that has a nucleum of helium and a neutron. Neutron has very high energy, which is what can give us, through the heating of water or cooling material, is what will provide energy. We have man can be a source of energy, and fusion can be a promising source of continuous energy without the emission of greenhouse gases. It is based on a nuclear phenomenon, so it's much more efficient. So for the same amount of matter, it can produce far more energy than fossil fuels, and it is suitable for industrial usage. So it is suitable to replacing electrical power stations or coal power stations, standard power stations. The fuel is these isotopes of hydrogen. The deuterium is abundant in nature. The tritium is produced in the reactor itself, and it is safe because, different from nuclear fission, which is the one now available in our power stations, nuclear power station, there's no risk of uncontrolled chain reactions, or there's a radioactive waste, but they are in high volume, but the radioactive level is far lower, so it's a different kind of management. And that's it. And now we're going to watch a short video to get introduced to the explanation of the experiments introduced with the jet.
You ready?
Yes. And is it going to work this time?
Are you confident, Fernanda?
Incredibly. We know the fusion works. It's not just a nice experiment. It's an experiment that can produce energy.
There's no question that if you crack it, problem solved for the human race.
I've worked on this for the best part of 30 years.
The last time we did this was in 1997 and broke records.
If we're going to solve energy problems long term, then we need technologies like this to do it. It's a really big challenge.
The challenges in terms of doing what is one of the hardest things on Earth to do, create a mini sun.
Oh, this is not so good.
We've been planning this for a long time, and it has to work. And if it doesn't work, it's on me and my unit.
We've got 3 weeks left. We've got to get it right this time.
In terms of being able to say that we've really pushed them forwards right up to its highest level, this is it. It's broken boundaries, but now it would be great for Jet to finish on a real high.
Ready to start the countdown. 5, 4, 3.
Just need it to actually work.
1, 0.
As we were saying, nuclear fusion and the experiments carried out with JET in the second half of last year have been covered by news media. But what happened during those days, those last 3 weeks? What was the important step that was made? And is it a surprising result some way, or unexpected, or everything went as per the plan? We have to go back to 1997. One of the things that we could see in the video is at the beginning, it's the video that we shot in 1997. We were really young. In 1997 and in the 90s, the first experiments with deuterium and tritium in tokamak were carried out in the magnetic confined machines. And that was a demonstration, for example, that the fusion deuterium-tritium worked and that could give some results. But those experiments also highlighted some physical phenomena that could be problems for reactors. And so from there on, a series of research studies started to make improvements, especially for the materials of the reactor, and in view of the creation of an experimental reactor that is called ITER, that is a worldwide project, some technological choices could be made in the jet. So in a small scale, jet seems to be this new reactor, and we could test these things with jet. So in 2021, jet basically is in a small scale, let's say half a scale, what ITER will be like. So the demo, this is the demonstration of the fact that not only did we obtain the results, but we went twice as further the results that we got in 1997. So in the first place, the technological choices that were made for ITER and that were installed in JET to test them work. So these choices, technologically and in terms of engineering, make sense. And then the other important thing is that all these experiments that we carried out in 2021 had been predicted. A number of calculations and some models were made before. We did them before, not after, and we set them aside. And then when we obtained the results, we compared with the predictions. And the beautiful thing, in my view, is that the predictions matched the results that we obtained. And some way it is a surprising thing in research. Well, it can be surprising because what we are simulating is a very complex system. It is not just about plasma. It's not just about the hot part, but we are also simulating the interaction of plasma with these cooler metal walls. And so there is a whole spectrum of physics from the center of plasma that is at 150 million degrees to the wall that is at 200 degrees in terms of temperature. So from this very hot plasma of hydrogen to a metal wall, and we managed in some way to simulate nearly all these processes.
After this result, what can we say? Where is the research standing? And what are the main scientific problems that need to be solved? Have you already defined some path to follow? Can you see the end of this project, or do you still need some innovation, some new discoveries to achieve these results? As I was saying earlier on, there is a machine. Well, I use the word machine, but I mean experiment. And it is being constructed in the south of France, and it is called ITER, and it is the following step. That is where we will try on a greater scale, almost as a reactor, these physical solutions. But we are still trying to answer some questions because, you know, the jet experiment is wonderful, but it is not able to answer these questions yet. So there are some questions on how this very hot plasma reacts with this cooler wall, and how we can isolate the wall from the hot plasma, because plasma is much hotter. And if there is a sort of radiation band where we have higher power, well, we need to isolate that part. Technologically speaking, there are two main problems. And I have mentioned them a little bit earlier on. First, the fact that the reactor's materials, after the bombing, let's say, of these materials, will become reactive. And so we will need materials that are suitable for being close to the plasma, and materials that do not become so much radioactive. And on the other hand, there is the fuel, tritium, and its reaction within the reactor. And these are the two main issues that only the new generation of machines maybe will be able to ask to solve. But the first experiments of ITER will be in 2026, 2027, so almost 10 years' time. This is a new generation of machines that will start giving us answers, but we cannot find answers yet. So this will be the next great step, but it is not the only activity that is actually in progress, right? No, because ITER is an international project, and it involves, I believe, about 80% of the world, in speaking in economic terms. China, India, United States, Russia, European Union, Korea, and Japan. So, all of them. In addition to ITER, there are some other associations involving both private and public bodies. In particular, there is a very interesting association. It is called SPARC. It is from the US, and Eni participates in it. And it is a meaningful participation with a very high level and advanced technology. In addition to the tokamaks, that is the magnetic confinement machines, we are also trying, or rather going back to other machines, always with magnetic confinement, but they are a bit different. So the number of experiments is growing, and we are not just experimenting on one machine, one line, but many. And as for other lines, there is an experiment in Italy that is called DTT. It will be built in Frascati, and it studies the interaction between the plasma and the wall. So this will be totally, let's say, devoted to studying this very important aspect for a reactor. And then there is also a machine in Japan, and it received contributions from the European Union. So ITER is the first big step, and all contribute to making it advance. And then the next step is that every partner of ITER will try to build the next reactor. So there will be one in Europe, it will be called DEMO, and one in China, CFETR. And then there are those who are less private, so to say. One is in the United States. It is called SPARC, with a reactor that will be called ARC. There are lots of acronyms. And then there will be one in the UK called STEP. So all these machines, all these reactors will be built. And while ITER won't produce any electricity, this generation, DEMO, STEP, ARC, will produce energy. So ITER will not produce any energy, but to be more precise, what is its aim? It is to produce more energy with the diffusion reactions than the energy we need to heat up the plasma. So, for example, if we use energy, an amount of energy to heat it up, we will need to produce energy that is higher. And at some point, the reaction is self-sustained, self-supports itself. So going back a bit and looking at all these situation, we can say that we know that the first research on thermonuclear fusion dates back over 50 years after the Second World War. I think that tokamak was created, the first one was created in the 60s. So more than 60 years went by. It is a very long period. It is as long as, well, it is longer than what we said yesterday evening about the Webb telescope, which required 27 years to be made. So why is progress so slow or so long? Why does it take so much time? Well, one reason was the lack of political will. There were some mistakes of scientific politics. For example, at some point in the project of ITER. The project was already quite advanced, but one of the involved countries, one of the main countries actually, decided to abandon the project. So the project didn't stop, but it was slowed down a lot. And I'm not telling now which country it is. And so, you know, dealing with all these changes for such a big project meant delays, lots of delays. And my impression is that even if fusion has been said to be an important, let's say, way to produce energy in 2 years, 5 years, or 10 years' time. So this is what was said. Well, but at the same time, the means used were very limited, the means of scientific, of university research. And in some cases, there was no connection with other technologies. So research was carried out, but advanced technology wasn't looked for and found, let's say, for a long time. And this is what has happened. So I mentioned Eni and the fact that it is involved in this work for the US reactor, this private-public reactor. And what is Eni doing? They are studying some magnetic coils that are superconductors, and they are high-temperature coils. And I'm not going to explain what it is because I'm not an expert in this field. But this means that, for example, these coils potentially consume much less than normal coils. And for example, the fact that Eni and other companies developed these coils was sort of spin-off and relaunched Stellarator, that is a line of research for magnetic confinement that had been abandoned in the 80s. And it was abandoned at the time because we thought that we didn't have the right coils to do it. But now that we have made progress, that there have been advancement, we can think of, you know, following once again this line and find an alternative to tokamak. So fusion takes some leaps. There was the first leap with the deuterium and tritium fusion, and there is this leap, and there will be this leap with high-temperature superconductors. But we are still talking about quite a long time before you mentioned ITER, which is supposed to be fully functional towards 2027. Are there ways to speed up this process, or does it require decades for inner reasons, intrinsical reasons? Maybe it will require decades for this reason. In the United States, President Biden held a conference, a meeting with the fusion experts in order to understand whether fusion could have an impact on the production of energy, and if this could happen in the short, medium, and long term. And in general, it was said that the first reactor that will effectively produce electricity and will put it in the grid, international grid, will be ready in the 40s, so 2040, 2050. Maybe this 2050 for the European reactor, whereas ARC for in 2040, but those are the years, the indications of years that we can give. Then there was another thing. A reactor was promised, or at least they promised to complete this reactor in 10 years' time. And this is not credible, in my opinion, because if we had the technology that we don't have, so if we had the technology to build power station, well, it would require at least 20 years. So a reactor producing electricity that can be, let's say, marketed takes much longer. And then in the future, there will be the industrial production. You know, the funny thing about fusion that everyone says when they talk about fusion is we will see in 50 years' time. It's not maybe 50 years' time, but it's 30. That's a realistic time frame. But there are realistic projects at the moment. So this leads us to make some personal remarks. Fusion is a very purposeful endeavor. So it's not just a matter of achieving progress in knowledge, but a useful result, a practical result. So a device that works and that gives some results. On the other hand, there are people working at this project, engineers, technicians, physicians, physics, so people who want their efforts to produce a result that is recognized and useful. So what makes it possible to hold on to such an endeavor, such great ambition, that it has a multi-generational duration, so it lasts for several generations? And well, you know, when you work for a goal that you know you will not see achieved in your professional life. Well, it is true, it is a long-term goal, and this is maybe what encouraged many of us to get into the research on fusion, and that is inspiring us. But it is also true that we work on small parts of research, and we see the progress made with those small parts. For example, we have been working, we worked in the past on 10 years projects, and in the period 2011-2021, we worked on the experiments on deuterium nutrition. So we somehow completed a cycle, and we will move to the next one. So if you divide the general research into chunks, into topics, into smaller and more manageable parts, it is also possible to, you know, be willing to keep on, because we are human beings, and so we are also encouraged by our desire to see our work published, our work recognized, so to speak in conferences. And this is something that we can do thanks to, for example, the parts of projects that we have achieved in 2 years. So a part of it that has been completed and is now over. And then if you turn back time in a way, and if you look back, for example, at 1997, we can see where we were at that time and where we are now, and see what has changed in terms of abilities, capacities. You know, it's not looking at the experiment and then the data and not know what to do, but we have a series of experiments that we can compare, and we can see what we have understood, what we haven't, and what we can improve or not. And so considering this, would you recommend a young person to get into this field of work? And would you do that on the basis of what motivations? And which kind of study or training would allow them to access this world? Well, to start with, I would recommend more in general to do research, not just in this field, any kind of research. As for fusion, I think that, well, my husband knows that there are days when you don't want to go to work, you know, because it's a fascinating, it's a fascinating job, and you are enthusiastic, and there is always something new. But there are those days which you don't feel like going to work, and then considering how the world of research is, I would recommend young people to do research because it is a very lively environment, a very lively context where you can exchange ideas, and there are new ideas every day. Some of these ideas are very valuable and some others are not. But it's an environment where generally you can respect others' opinion. It is not easy. I'm not saying it is easy, but you always try to respect also young people's opinions. Unfortunately, not all fields, not all environments are like this. I think I'm lucky because, you know, in our lab, the pay is not very good, and so we need young people and we need newly graduate to, you know, get to work, and we immediately entrust them with tasks and responsibilities. And as Spider-Man used to say, if someone entrusts you with a task, with a responsibility, you have to take it seriously. And so this is what happens in my lab, but there are other fields, other environments, especially the most academic ones, where it's different. There is this hierarchy with more difficulties for younger people to make their voices heard. They told me that I ran away, that I'm part of the brain drain. I studied in Milan at CNR, and then 6 months later I went away. I had a 1-year scholarship, and that scholarship went longer. It went up to 2 years, and then I have never come back. So my recommendation to young people would be to get the degree, have experiences even abroad, and then see. And if the right conditions are met, go back to Italy, because research also happens in Italy. Very good research, excellent research is done in Italy. For example, of the DT fusion or other studies, physics. Well, these are incredible. It is incredible research also in Italy. Otherwise, if you don't like what there is, go abroad.
Is there any scientific areas that is particularly relevant in this respect? Well, one of the things that characterize research about fusion is that physics and engineering go hand by hand. So the progression of one makes the progression of the other possible. And for example, in other meetings in our laboratories, physicists and engineers work together. So a degree in physics or a degree in engineering or a PhD if possible. I do not have a PhD. I started without a PhD because my father told me, come on, you have to start gaining some money at some point, but a PhD for sure. And both physics and engineering and physics can be experimental or theoretical physics. There are excellent Italian scholars in theoretical physics and excellent Italian scholars in experimental physics. Well, you described your career, and we know that frontier state-of-the-art work is challenging on a personal level. Now, it's not easy sometimes to just leave and go abroad. So how do you reconcile all this job with the rest of your life? For example, personal relationships or relationships with the loved ones, with the family? And in particular, is it more difficult for a woman to be intensively busy in scientific research? Well, I start answering the second question that is possibly easier. It is difficult. It is still difficult for a woman to be intensively busy and to be acknowledged much more well, less than in the past, in fact, in general. If we consider Europe and the world, there's women who are PIs and are heads of laboratories, and they PIs of important research groups. So we managed to get a bit higher on the scale. And when I started, there were just few women. I was lucky enough to go to work to the United States for 6 months, and it was I myself and there was another woman in another laboratory. So when I arrived, the number of women working there doubled, but now it's different. There are many more women. And now I'm about to say something that you may not think about. In the past, to work in fusion or in research, somehow you had to pretend to be a man. So to get dressed in a very standard way, let's say, without showing off. Now it's not the case. You can be whatever you want in terms of sexual orientation. You can have a tattoo and nobody will make a fuss of it. And so the environment is broader, and this is helpful. And one can feel at ease, and it's easier to do research. Having said that, when I had my second son, I had a maternity leave for a couple of months. And then I restarted working at the end of the year. And I had the overview with my boss, the year overview with my boss to see what I did. And we're not talking about the 19th century, I'm talking about 20 years ago. And he told me clearly, you know, this year I can't really apply for any promotion for you because you just worked for 6 months. Fair enough. So some things do still happen. And this brings me to talk about the relationship with my family. I work with my husband. I work in the same laboratory as my husband work. We got to know each other there. And one of the reasons why we're still together, despite the fact we are a little bit weird, we have a difficult kind of character, is that we understand how important research can be for the other one. Sometimes we have a problem that may be unsurmountable, and it takes us so much that we keep it with us on, and we have it in our mind continuously, even when we are at home. And since we work, the two of us, in the same place, we understand these things, we can talk, and this was really helpful over the last 2 years during the pandemic, because many colleagues of mine, they were at home working on their own during the lockdown, but my husband and I, could keep talking directly and have our dialogue. And we still had this desire to continue to talk about work. But then at one point one has to stop, because there's the children and the family members, and it gets to the point that we have to take care of the family members too. In some periods, I have an almost normal life, like over a weekend, on a Sunday, I do normal things. But there are other times when I work on a Sunday, on a Saturday, if we have deadlines, and so it's okay. We work also during the weekends. There's some evenings when I get home very late. I have shifts, so sometimes I get home at 10 in the evening. And my husband, who is not Italian, learned how to make pasta, to cook pasta. So I get home and I find a nice plate of pasta, and it can help.
Senti,
could we say what would change in a world where a big part of energy were produced with the fusion, nuclear fusion? In which sense would it be a better world? Well, to begin with, it would be a world where most energy would not be produced with greenhouse gases fuels. So we would have managed to stop this climate emergency, or to manage it. We probably won't be able to get back, but we would be able to stop the crisis, the climate crisis, without losing our lifestyle that is based on an intensive energy consumption. Because the alternative, if we do not have energy, is to go back to a far more primitive lifestyle. We have these wonderful applications, screens and smartphones and devices that are connected, and they all consume energy. We are now saying that we're going to use electric vehicles, and they all consume electricity and energy. So the risk is that we would have to renounce to these things and to our Western-like lifestyle, but not just us, also developing countries, the countries that are about to arrive now, which is not their fault. We've had a wonderful life over the last 100 years, and we took advantage of that, and now we're saying to the others, no, you can't do the same because there's global warming. Well, having these energy sources, these fusion power stations, nuclear fusion power stations, along with solar energy and wind energy and hydroelectric energy, all this would give us the opportunity to continue with a development that provides us with a comfortable and pleasant life. We have heat in our houses, and at the same time we could give the same opportunity to the others to follow through or to join us in a similar kind of pattern. One last point I would like to mention is related to this. Now we see the importance of energy dependence at an international level, and this really highlights the critical situation of countries that are not independent in this respect. Will nuclear fusion allow for greater autonomy in this respect, or could it be just a different kind of dependence, a technological dependence? In my view, there are two kinds of countries that we may talk about. There are the 7 partners of ITER that I mentioned. Each has its own project for a reactor, so the technology is being shared, the technology developed in ITER for the next reactor. So considering Europe and the United States and also countries that are growing, such as China and India, these countries are likely to have the technology because they are taking part in the ITER project and they are among the countries that contributed a lot to this development. So from this point of view, there shouldn't be these technological dependencies for these countries. What is the risk? The risk is that technological dependence be for countries that are not as developed. And so if there is the need to build a power station, they have to have that built by others. But what is the advantage? Now we could build fission power stations that have specific risks, and this cannot be disregarded. But the idea is that a fusion power station has lower risks and is easier to manage in case of accidents. These will have minor consequences, and so these power stations would be easier to manage. Also in terms of human resources, the requirements, the demand would be much lower. Thank you so much. We're about to close the session. Thank you, Dr. Rimini.
Grazie.
Thank you. Thank you for this highly interesting conversation. And to conclude, I would like just to review some remarks in order to consider them and following what we have heard. First, looking at the last remarks that we've heard, is that we cannot really consider our easy situation for our societies. We cannot take it for granted. It is a privileged situation somehow. And the idea is not to keep this privilege, but to allow others to enjoy the same opportunities. So that's part of a civic and a Christian commitment, and it is a serious research commitment too that is required. And then more specifically, I would like to emphasize the importance of teamwork that you have mentioned a few times, and also interdisciplinarity. That is the ability to work and taking the best out of all the persons involved. Another point that I found interesting is this combination of predictability and surprise. There is this objective of creating an object that has to work, and one does not really want to have unexpected results and bad surprises. One would wish to have something that is as close as possible to what has been planned. And we've seen these good results in the experiments you mentioned with a matching between the predictions and the results. I think it's really, really significant. And we have also appreciated the importance of the scope of the change in the world panorama that this kind of scientific discovery could bring to our society, so reducing environmental impact, reducing energy dependence, and contributing to reducing inequalities between the different parts of the world. Of course, all this does not happen automatically. What is necessary is to have a well-founded and shared passion for the person to make a scientific result, a scientific tool or a technological tool, a real opportunity for good for many. Another aspect I would like to highlight is perseverance. Perseverance in a field that by its very nature requires long-term perspective and collaboration of generations with other generations. This is certainly a crucial point in a society where often the main model is the immediate result. It is the loophole strategy. And eventually, there is this other point that leads us back to the theme of the meeting of this year, a passion for the person. And I would like to highlight the importance of the nuclear fusion enterprise in the sense that it is an internationally shared effort. So it provides a privileged opportunity to dialogue, to sharing, also among very different cultures in their approach to working. And we've seen this many times in our professional life. And this level of dialogue and exchange and collaboration in such a difficult endeavor is something that is really important, that it is so much needed. Talking and having a dialogue and talking together instead of using loopholes and other underground strategies. And with this, we can close this session. And tomorrow, Fernanda will be available at 12:30 in Arena Scienza in the Hall C1 for the series of events to continue a meeting, to continue a session. And in this time frame, the audience will have the opportunity to ask questions and to interact with the speaker. In this international effort, our country plays a crucial role with one of its main research institutions that are included, that include in their programs activities that relate to the development of fusion, such as ENEA, the National Agency for the Development of Energy, and CNR, other research consortia, such as RFX and the CREATE consortium, and other groups of university research and other industrial entities have also joined this ambitious venture, such as Ansaldo Nucleare, Rina Consulting, Eni, Nier Ingegneria, and I just mentioned those that are listed, the biggest ones. And in tomorrow's session, to understand more this subject, we will have also Pier Giorgio Sonato from the University of Padua that will give an overview of the activities that are ongoing in Italy for this aim. And finally, please remember that opportunities such as this one are possible in a cultural event such as the meeting. That is possible thanks to the work of many volunteers, a lot of work over a lot of months, but that's not enough. Also, financial resources are needed. So I would like to remind everyone of the opportunity to donate a contribution. You can do that at the Dona Ora desks with the red heart sign. You see volunteers wearing a red T-shirt, and you can donate your contribution there. And this year you can also have a tax relief program there. Thank you again for your attention.
Civiltà dell'amore, fratelli e sorelle, costruite senza stancarvi mai questa civiltà. Lavorate per questo, pregate per questo, soffrite per questo.